So, so when we're looking to construct a free body diagram, in this course, we're interested in the effects of the external forces on our system. So sometimes there may be, in our systems, there may be some internal forces that are applied to our rigid bodies. These include things like screws, bolts, and welds, which apply internal forces that are meant to hold different components of the rigid bodies together. So typically these forces are going to cancel one another out, so they'll have like an equal and opposite force. So they're not going to cause the body at all to rotate or translate. So we're going to ignore these types of forces when we're constructing our free body diagrams of this course. Um, then another consideration that you need to think about when you're drawing a free body diagrams is the weight of your rigid body. So you need to make sure you account for the weight of the rigid body within the diagram. And then the weight is always going to be applied at the center of gravity of the rigid body. Typically, a lot of times we'll be working with materials that have uniform density. So the center of gravity is going to occur at the centroid of our shape, or the center of volume. All right, and then the last thing we're going to talk about is, or one of the things we're going to talk about is idealized models. So sometimes, like a lot of times, if you look at an engineering component, there's they're rather complex. Okay, so they have multiple parts. They have a lot of loads that are being applied to them. All right, so oftentimes when you're analyzing a design, you want to just simplify it to some idealized solution to the problem. Right, you're going to create a model of the problem, try to analyze that model, and then see whether or not you can identify any flaws in the current design so you can modify it or improve upon it. So here are we're going to do a couple quick examples of creating an idealized model of some real situations. So in this example problem, or in this example, we have a beam that is supported at 2 points, at point A and point B. Right? At point A, we have the rigid body, the beam is bolted down to the wall there. So we're going to say, all right. And at point B, it's just it's just allowed to rest at point B. Okay. So due to those two supports, we have at point A, it's not like cemented into the wall. So those bolts, though they'll apply a force to keep it in place, they're not really going to prevent the beam from rotating that much. So we're going to treat it as a pin support. So we'll have f of x and f of y at point A. Okay. And then at point B, we'll treat this contact as a smooth roller contact. So I'll pretend it's a roller. All right. And we'll say that this is just going to be equal to a normal force that's applied at B. Okay. All right, so we drew our rigid body, we drew our support reaction. So we're going to now draw our external forces that are being applied to our system. Okay, so in this case, we're going to say we have the weight of the beam, and we'll assume that the beam has a uniform density across it. So we can say that this would be applied at length over 2. And then we have 3 beams that are supported by this smaller beam from point A to point B. So we can say that these 3 beams would apply 3 forces, F1, F2, and F3 on our system. All right. All right, and then the last thing we would do is we would apply our equilibrium equations. So we would sum all of our forces in x, set that equal to 0. We would sum all of our forces in y, and set that equal to 0. And we would sum all of our moments about a point. So in this case, we would sum maybe about all of moments about point A and solve for that. Using those 3, we'd be able to solve for fx, fy, and fc. Or sorry, fx, fy, and and B. All right, for this situation. All right, so that was a simple one rigid body case. We can also apply it to a system of rigid bodies. So in this case, we have a crane here. All right, the crane has two components. It has a component that starts at point A, all right, and it goes up to the top of, I guess, the crane where the operator would sit, and then at point C, we have a small link, which is a hydraulic which is a hydraulic cylinder. All right, that connects with the member with the long arm of the crane at point C. All right. So now we have the outline shape of our rigid body drawn. We can apply all of our support reactions. So we know at point A that it has to allow for rotation of the crane in order for the crane to be supported. So we can treat, for the crane to be functional, it has to allow for rotational motion. So we can say that this would be equal to A, would have two forces, A of X and A of Y being applied at this point. At point B, we know the hydraulic cylinder would also need to be able to rotate in order to operate the crane. So we could write this as B of X and B of Y. And then we know that for a hydraulic cylinder that it will always apply a force that will go along its axis. So we know that the hydraulic cylinder would need to apply a force in order to support the weight of the crane. Otherwise, the crane would rotate downwards. And we know it'll be along its axis. So we'll say that there'll be a force FBC that would be applied to the arm of the crane in order to keep it supported. And we know that there would be an equal and opposite force that would go in the opposite direction downwards on top of the cylinder. Okay, and then the last thing we would do is we could apply our external forces. So there would likely be a force due to the operator who's sitting here. Right, that would be our operating load, and then there would also be the weight of the crane arm itself that would be applied at the system. All right. So if we treated these two rigid bodies as separate systems, so if we isolated, so we could isolate just the crane arm, all right, and the hydraulic cylinder. Okay, we could solve for all of our unknowns. So we could solve for AX, AY, FBC, B of X, and BY. Right? All right, and we'll get a little bit more into those problems soon, especially next lecture. We're going to go through the whole process of doing the free body diagram for the equilibrium. But the main thing we wanted to focus on today is just drawing the free body diagrams accurately based off of the given information.